Okay, so second part we're going to look at on vectors, we're going to focus more on like calculations, not as much drawing. The only drawing we will do is a word problem, okay, when we get to that. We'll do a little bit of sketching to kind of figure out what the formula is. But even once we know the formula, we really don't even have to keep sketching. We're just going to use a formula. So not as much sketching today. All right, so I'm starting out with two vectors that are in, we call that algebraic notation, where we use angle brackets and then two numbers separated with a comma. The first number tells you a horizontal component. The second number is a vertical component. Okay. And if you're not quite sure what I mean by components, imagine you had something like this. Okay. You got a vector that starts here, ends here. Basically, if you make a right triangle out of it, that's the components. So just make a dotted line, goes that way, and that way. So this particular vector would have a vertical component of 1, 2, 3, and a horizontal of 1, 2, 3, 4, 5, 6, 7, 8. So if you were going to write this vector down, the way you would write it, just like that, 8, 3. What that notation doesn't tell you is where to start. Okay, so you could start here and go 8 right and 3 up. You could start down here. You can start anywhere you want. But when we have axes, we usually start at the origin. Okay. Okay. So the idea of what it means for two vectors to be equal is that the horizontal components match and the vertical components match. Okay, they each match. So that might seem like kind of obvious, but let me sketch something on the next page and just show you exactly what that means visually. Okay, so it says when the x's, x1 and x2 are equal, and y1 and y2 are equal. So I said you could draw this vector starting from pretty much anywhere. So let's start here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Those two vectors that I have on the grid, they're the same vector. They have a different starting point. Like if you gave the coordinates of the initial point, they're different. And if you gave the coordinates of the terminal point, they're different. But that's not what it means for vectors to be equal. Doesn't mean that they're right on top of each other. It just means if you went like this, they have exactly the same horizontal and vertical components. And of course, if you did drag them so they were right on top of each other, they would look like they're the same. Okay? But for vectors to be equal, they do not have to start and end in the same spots. That's all. Question on that idea? Okay, so that's really the only thing I'm going to say about vectors being equal. That's it. All right, so we've talked about how to represent vectors as an arrow. We've talked about how to represent them using that algebraic notation with the angle brackets. I'm going to show you the third and final way, probably the most common way, and that's called unit vector notation. Okay, we talked about that word a little bit yesterday when we were talking about length. Okay, the word unit vector. Does anyone remember what that means? If a vector is a unit vector? Yep, that's one. It's one what? Not one point. Maybe more specific, like one what? Yeah?
It has a magnitude of 1.
Yes, it has a magnitude of 1, which means basically it is a length of 1 unit. So I'm going to show you guys two special unit vectors. So yesterday I said there's certain letters you would not want to use to name a vector. Okay? Usually the way we make a letter look like a vector is we make it bold, or we put an arrow over it. Well, there's two letters that you don't want to use for vectors, and it's not because the letters look like numbers. Like I said, stay away from using the letter O because it looks like a 0. But here's two letters I'm going to give you that are kind of special, and you would never use them except for what I'm showing you right now. One of them is the vector I. Has nothing to do with complex number I. So it's a bold I. And the vector I is just a special unit vector that points one unit to the right. That's all. Vector I is a unit vector and it points to the right. So if you had to name a vector on the test or in the homework or anything, you would never use the letter I, unless you're talking specifically about that right there. That's the only time you would use the letter I. Okay? So I points to the right. Now, what do you think I could do to I if I wanted a vector that pointed to the left one unit? Because I points right, but sometimes I might want one that points left. Yeah, yeah, just throw a negative in front, and now negative I would point to the left. Okay, so we got left and right covered. One other special unit vector is the vector J. So J is another letter. You would never use that to name a vector you're dealing with. Only time you're allowed to use J is if you're talking about a unit vector that points up. And likewise, what could I do to that if I wanted a unit vector that points down? Yep, make it negative J. So between positive and negative I, positive and negative J, you've got left, right, up, and down covered. You've got all the different directions you could go covered. All right. And here's the vector J. It's one unit long, and it points up. Okay, so how are we going to really use I and J's to write down vectors? Well, the idea is think of I and J as like Legos or like building blocks. You can stack them together to make a vector. Right, so that's what we're going to do. We're going to stack I's and J's together to build a vector. So this part is a little bit visual. Once I show you how it's visual the first time, we're not going to draw it out again. Okay, just the first time. Okay, so let's look at the vector 3, 4. Right, if I wanted to draw that vector 3, 4, I would start at the origin, and I would go which way? And how many units? Yep.
Go right 3.
Right 3, okay. Anything else?
Up 4.
And up 4. Right 3, up 4. So think of that as where you want to end up. Okay, that's where we want to end up, and we're starting at the origin. So we're going to try to build that vector in black. All right, let's start with the eyes. Okay, and I'll make them red so we can see them a little better. How many eyes would I have to stack together, starting at the origin, to start to get towards that terminal point?
3.
I would need 3 of them. Yep. So I'm just going to make 3, and I'm going to go like this. I got 1, 2, 3. So the new way that we're going to write this vector, the first part of it is going to be 3i. That's the first part. 3i. But now we need some more. How many j's would I have to stack together to get from where I'm at now up to the terminal point?
4.
4 of them. So I'm going to take, let's just make these, make those green. So we got 4 of those. And now we're just going to stack them all together. 1, 2, and 3. 1 more. 4. So that part is 4j. So now what we basically have is this. There's 3i. here is 4j. What did I do with 3i and 4j to make that vector that's on an angle? But right now, they're just two separate, like here's 3i, here's 4j. Anyone tell me what I would have to do with them? Okay?
Add them.
Add them, yeah. Just add them together, just like that. And if you add them together and draw in the diagonal, that's exactly what I have in black right there. So, add them. So that's the last way that we're going to learn how to write vectors. That's called unit vector notation. 3i plus 4j. Now it could be a minus, like if you had to go over here. Well, now you would need negative i's. You would need negative 1, 2, 3, negative 4i plus 2j. That one would be up here. So basically, no matter where I put a point, over here, 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 up here, I can get to any one of those points that I just put on the board by stacking together i's and j's. Now, I might need half. That's okay. If I only need to go down like 1, 2, 3, 4.5, so that would be negative 4.5j. So I can get anywhere that I need to by stacking together i's and j's. Sometimes positive, sometimes negative. Maybe I need a fraction of an I and a j as well. Any question on that idea? So, since you can get anywhere you want, the fancy word for that is span. Okay? Vectors I and j allow you to go anywhere you want, or they span the entire plane. Now, when we get into 3D, I and j aren't enough. I and j, think of like this table as the xy axis. You can move anywhere you want on the table. But when you get into 3D, you also have to be moved off the table, up and down. So we're going to need a third unit vector to be able to move up and down, or in and out of the board. Anyone have a guess what the third vector would be called? Yeah?
K.
It will be k. So I is the unit vector on the x-axis. J is the unit vector on the y-axis. K will be the unit vector on the z-axis. We don't have to worry about that yet. All right, so let's look at some formulas for vectors. All these formulas that I'm going to give you, they're going to have, some of them will have up to 3 things in them. If you see a v and a w, those are vectors. If you see alpha, that's a scalar, okay? Just a number.
Is there any reason why it's those 3?
Why they use the letters I, J, K? I don't know. The I, J, and K aren't short for anything that I know of. So I'm not sure why they use those particular letters. It's kind of maybe like in Pythagorean theorem, they most of the time use A, B, C. It's not like A, B, and C stand for anything. Like apple, banana, and cars. They just used A, B, C.
Because the person who came up with the math equation went to IJK.
Yeah. And I guess the good thing about I, J, and K is if you draw them, they don't really look like other numbers. I mean, the closest thing is I, you could maybe say it looks like a 1, but if you put a dot on it, it doesn't really look like a 1. So. All right. So first formula I'm going to show you is for adding 2 vectors. Okay. If you want to add 2 vectors the old way, okay, for those that weren't here, this is how we did it yesterday. You draw a vector. You draw another vector. Then you'd have to line these vectors up like that. And then the last step would be to connect where you started to where you finished. So that would be the answer when you add the 2 vectors I just drew. Well, a lot faster way to do that is with just numbers. To add 2 vectors up, all you have to do is add the horizontal components together, whatever those 2 numbers are, comma, and then add the 2 vertical components together. So that's going to take the place of all the sketching we had to do yesterday when we added. Subtracting is very similar. If you want to subtract 2 vectors, subtract the horizontal components, the x components, and then subtract the y components. Now with addition, the order is not really important. If you add 5 plus 2 or 2 plus 5, it doesn't matter. Subtraction, the order matters. If it's v minus w, make sure you do the x value from v minus the x value from w in that order. Same for the y's. Okay, so that's adding, subtracting. Okay, what do we call this when you multiply a number times a vector? That was in the homework. Yeah, that's a scalar. Alpha is a number. Okay, or if you want to be more specific, we call it a scalar. Well, the old way we had to do it is like if you had a vector, let's just say v, and you wanted to know, well, what's 2v? Well, you had to take v, you had to copy it, put it together, and then trace over it, and there's 2v. Now we don't have to do that. You can almost think of a scalar product. It's almost kind of like distributive property. You take whatever you're scaling by and multiply the x component by that number, and then the y component. So you just multiply each component by the number. So it's kind of like distributive property. And then the last thing, we talked about that symbol yesterday, and I kind of showed you how you would do it. I said we'd actually do one today. But what does that symbol mean again? When you put the double bars around a vector? It means magnitude. And does anyone remember what formula I said you basically use to find the magnitude? Yeah? Yeah, and we did it kind of right here. If you wanted to know the length of this vector in black, make a right triangle, take the horizontal component, square it, the vertical component, square it, add them up and take the square root. So you just do the Pythagorean theorem. And here's the formula. I just used the x and y because that was the horizontal and vertical component. That's what we named them. So that's really just the Pythagorean theorem. So we'll go through one of each of those formulas right now, but you shouldn't have to do any sketching for any of this. Okay? No sketching at all. Now, I also want to practice writing the answer the old way with the brackets and the new way with I and J. I mean, if you can write it with the brackets, the I and J is pretty much the same thing. It's just like you're taking the comma out between them. Take off the brackets and just put the I and the J with each number. Okay, so let's add these vectors up. Let's do that first. So Isabel, for vector v, what number is the horizontal component? 2. How about for vector w, what number is the horizontal? 3. Now if you combine them together, a horizontal component of 2 combined with a 3 gives you 5. So when you add these up, the horizontal is going to be 5. And Nick, how about the vertical? Yep, -1. Perfect. So you can write the answer like that. That's fine. Or we can write it with ij, okay, unit vector. Connor, could you tell me how I would write that as unit vector?
2y minus 3j.
For this one?
Oh, 5i minus 3j. Or 1j. Oh, wow, I'm really screwing up. Sorry.
So you got 5i, yeah, that's good. And what did you say the other part was?
Minus 1j.
Minus 1j. What else do you think you could put besides minus 1j?
Minus j.
You could just put minus j. Okay, either way, you get the answer right. Okay. And again, some people that weren't here, you might be wondering, why is he tracing over his I's and J's and making them darker? That's because these are supposed to look bold. It's one of two ways to make a letter not look like a variable. Okay, so that's adding them. Let's look at subtracting. Okay, so Kylie, if I subtract the vectors and I go v minus w, what would the horizontal component be?
-1.
Yep. Can you say it again?
-1.
Yeah, -1. Okay. So we get -1, comma. And Greta, how about the vertical component?
7.
7, right? You gotta be careful there. 3 minus -4. Minus a minus becomes a plus. Okay, so we can do it that way. Or let's write it as a unit vector. So Emily, how would I write that as a unit vector?
-I plus 7j.
Yep, that's it. -I plus 7j. Okay, so that's adding, subtracting. Let's look at this one. Scaling. Remember, 3 things can happen when you scale a vector. Longer, shorter, flips direction. Is this one flipping direction? No. How do you know that, Jake? It's not a negative. That's all. So we're going to take vector v, and we're going to triple the length. So Emily, if I take vector v and triple it, what would the horizontal part come out to?
6i.
Yep, and the vertical?
Oh, 9j.
9j. So 6i plus 9j. Or, if you wanted to write it, 6, comma, 9, but don't mix the two, all right? If you write it with the brackets, you don't put letters. You just put numbers. Questions on that? Okay, and now let's look at this one. The magnitude of v. All right, so Sam, if I want to find the magnitude, can you tell me what I would write down first?
The square root.
Yep.
I
I would start with the square root.
Of 2 squared plus 3 squared.
So
Or
2
2i.
squared.
Yeah.
Yep. 2 squared is 4. 3 squared is 9. So it's going to be 4 plus 9. When you're finding the magnitude, just think of it as Pythagorean theorem, just using numbers. One side is 4, other side is 3. One side's 2, one side's 3. So 4 and 9. So the magnitude is the square root of 13. If you could reduce that, you would. If you got the square root of 20, I would want to see it as like 2 root 5 or something like that. 13, square root of 13 doesn't reduce. So if you look at all the answers, all the things that are circled, one of them is different than all the other ones. Which one is different? D. Yeah. What's different about D in terms of the kind of answer that you got? Yeah.
Doesn't involve I or J.
So what does that mean?
What's the length?
It's what?
It's the vector.
What's a vector?
The square root of 13.
No.
Is it a magnitude?
It's a magnitude, right? D is just a length. It's just a number that tells you how long something is. AB, what are A, B, and C?
Vectors?
Those are vectors. Okay, so A, B, and C are vectors. You can think of those as arrows. D is not an arrow. It's just a number that represents how long something is. So D is a little bit different kind of answer. All right, let's look at this. So, just a reminder, if you already know that, you don't need to write it again. But if you have a vector that is a magnitude of 1, it's called a unit vector. So I guess U is another special letter that usually you use the letter U when you have a unit vector. Okay? So I is a special one, we don't use that letter. J is a special one, K, but you don't know that one yet. and U. That's another one we usually don't use the letter U. But any other letters are fine. Okay, you're not really going to need the diagram. I'm not going to use it. All right, let's say we had the magnitude of a vector. And I want to know what to scale it by to force it to become a unit vector. So let's say you had a vector 5 units long. To be a unit vector, how long should it be? 1. So what could I scale 5 by to make it 1 unit long? 1/5. Okay. What if I had a vector 8 units long? What could I scale it by to make it 1 unit? 1/8. Okay. What if I had a vector 1/3 of a unit? Yeah? 3. So what's the pattern? Does anyone see? You're multiplying by the reciprocal, exactly. It's all you have to do. If you have a vector and you want to change it into a unit vector, you multiply by the reciprocal of the length. So what if your length was x? You'd multiply by 1 over x. Yeah. Okay? So that's how you find a unit vector. Let's just put that into a formula. All right, so when we're finding a unit vector, all you're doing is taking a vector you already have and making it a little bit shorter or making it a little bit longer to make it exactly 1 unit. You're not changing the direction. Okay, so you're just taking a vector and making it a little longer or a little shorter to force it to be 1 unit. But it still points the same way. Okay, so the formula, we said multiply, I heard someone say multiply by the reciprocal. This is the same thing. If you take, this is the way you guys told it to me, just take your vector and multiply by 1 over the reciprocal of the length. Well, that's the same as just dividing by the length. Think if you take 3 divided by 3, or 3 times 1/3, it's just the same thing. So multiply by the reciprocal, that's one way to say it. Divide by the length. Either way, the length is in the bottom of a fraction. Okay? So we're gonna try that. I'm gonna give you guys a vector, and I'm gonna want you to turn it into a unit vector. So first thing you always want to do is check the length and see if it already is a unit vector. If it is, then there's nothing to do. If it's not, then we gotta scale it so that it is. Maybe that means make it a little longer, make it a little shorter, but you gotta make it 1 unit. Okay, so we've got the vector 3i minus 4j. So in order to know if that's a unit vector already, what do I have to find? Yeah, find the magnitude. And even if it's not a unit vector, finding the magnitude is going to be the next step to making it a unit vector. So finding the magnitude is not a waste of time. You're going to need it. So let's find the magnitude. Okay, so I always start with the square root so I don't forget it. And what's going to go under the square root? What plus what? 9 plus 16. 3 squared. And then negative 4 squared. So this vector is how long? 5. Okay, it could have come out to a square root. This one didn't. I just picked a nice number to have it come out to. So now we can answer the question. Do I have a unit vector? No. What would I scale it by to make it a unit vector? 1/5, because it's one of the numbers we wrote right here. If it comes out to 5, scale by 1/5. Okay. So you've got 1/5 times v. What's v? 3i minus 4j. So if you take 3 and multiply by 1/5, what do you get? 3/5. So the I component becomes 3/5. And what about if you take -4 and multiply by 1/5? -4/5. Yep. So all you basically did was divide each number by 5. 3/5, 4/5. And that's it. If you wanted, what's that?
That's not like number 1 though, so now I'm confused.
Well, the length of it would be 1. Like if you used the Pythagorean theorem on this now and checked it to see is that 1 unit long, it would be. Because if you square 3/5, you get 9/25. And if you square 4/5, you get 16/25. 9 and 16. So the length of that vector is the square root of 25 over 25, which is 1. So this is now 1 unit long. We just made it 5 times shorter. Does that make sense? Okay. Other questions on that? Any question on how you'd write it with the angle brackets instead of I's and J's? Okay. So, last thing we're going to look at is it's kind of like a word problem, but it's actually, once we draw the diagram to get the formula, you're actually never going to need to draw for this type of problem again. And what we're going to do is come up with a formula for what's called a velocity vector. Okay, so first thing I just kind of want to think about is if I were to throw an object like this, and say this is the ground, which way is that object traveling if the arrow represents me, me throwing the object? It's going up and to the right. I know gravity would bring it back down, but that would kind of complicate it. So we'll just assume that it's like a vector. It just keeps going. So we're doing it in outer space with no gravity. We're away from any planets, at least far enough away that it would just keep going straight. But the important thing that he said is it's going in 2 directions. It's going up and it's going to the right. So when you write a velocity vector, that's basically what you have to find. What's the up part and what's the right part? All right. Now, sometimes when you throw something, it's pretty much just one part. Like if you think of like a pitcher throwing a baseball, they don't really throw the ball up. They pretty much, it's very straight. Maybe it drops a little, but it's pretty straight. Because the straighter they throw it, the more energy goes into throwing it forward. They wouldn't pitch the ball like that. It wouldn't be coming at the person very fast. It would be like coming straight down almost. So they pitch it as straight as they can to put all the energy into the horizontal, very, very little energy into the vertical. Okay? If you had a cannon and you were trying to hit a target, then you might have to give it some vertical. Maybe there's a wall and you got to clear the wall to hit whatever it is you're trying to hit. You can't. The cannon's not powerful enough to maybe go through the wall for whatever reason. All right. So we got to figure out the components. So let's start with this. So what I've got here is a vector on an angle that just represents an object traveling up and to the right. Any question on that? All right, I'm going to give some names to some things in a second. But for now, I want to turn that into a shape so I can see its components. I want to see its horizontal and vertical separate. So what shape can I turn that into? Sam?
A right triangle.
A right triangle. Yep. So we're going to draw a line straight down. And now we can look at what the components are. In red, that is your horizontal. Okay? That's the part of the vector in black that's actually traveling horizontal. This is the part of the vector in black that's actually the vertical. combine the red and the green together, and you get the one in black. That's what we did yesterday. Questions on that? Now, when you throw it in the problem, they're always going to tell you an angle that you throw it at. That angle, there's a couple different names for it, but most of the time they just call it angle of elevation. And I think actually the formula in your book, they use alpha to represent the angle. It doesn't really matter. It's like in algebra picking A instead of B for the letter. It doesn't really make a difference. But they'll tell you the angle. Okay, so now we need to label some of these sides. So let's let x be the length from here to here. Let's let y be the length from here to here. And now I'm going to name the vector in black a little different. I'm going to do it the way your book did. I'm going to call it vector v. So the red one I've labeled as x. That's a length. The green one I labeled as y. That's a length. The black one, I just labeled it as v. That's not the length of v. It's just the thing that you're looking at right here, the actual object. Okay. Questions on that? All right. So now what we have to do is figure out a formula for that vector in red, and then figure out a formula for the vector in green. So basically we're going to do this. Red vector plus green vector equals black vector. Okay, so we're going to focus on this. We want to come up with a formula for the black vector, because the black vector represents the direction the object that you threw is going. So let's start with the red vector. Well, which way does the red vector go? Horizontal or vertical?
Horizontal.
So when we're done, we're going to have a formula for the red vector, and it's going to have an I with it. And the green vector is vertical, so we're going to find a formula for the number, and what letter is going to be after the vertical number. It's going to be a J. All right, so it's going to be something with an I plus something with a J. Let's start with, these three things. What's the name of, if you think of this as a right triangle, what's the name of the side that we've labeled X?
Adjacent.
It's adjacent, yes. So I'm just going to write that off to the side. And what's the name of the side we labeled V? Hypotenuse, yeah. So adjacent is the side we labeled X. Hypotenuse is the side we labeled V. What trig function involves those two? Adjacent and hypotenuse. What is it? Cosine, yes. So let's write that down. Cosine of, what would go in parentheses? The cosine of theta, it's always the cosine of your angle, equals adjacent over hypotenuse. X is the adjacent. Now, what did I just say goes in the bottom here? What about the hypotenuse? Like the color, should I put like black down here? Because that's the hypotenuse, it's black. So it's the length, yes. It's the length of the hypotenuse. So how do you represent the length of the hypotenuse? Well, we've got a name for the hypotenuse, so we want to use that name, but it's not just that. Because this is bold.
V equal
The x and the y are not bold. Those are just lengths, yeah?
the magnitude of V.
Yes. The magnitude of v. X was already a length. Okay, that's the way I named it. Look at the way I drew it. I drew those little arrows and those lines to show you X is the length. I didn't do that for V. Okay? V, I just called it a vector. Now, how would you get X by itself? And that's going to be the formula for the red vector. Yep, multiply the magnitude times cosine theta. There is the formula for your red vector. Okay, so let's start to put that down here. So we've got magnitude of V, cosine of the angle, pi. Okay, so there's my red vector, plus now I need my green vector. I know it's going to have a j, but we got to figure out what goes in front of the j. Okay, so now let's focus on what I'm circling. Actually, let me get rid of these other circles. Just focus on what I've circled in red. I've still circled hypotenuse, so we're still using that side. What about y? What side is that?
Opposite.
Opposite. Y is opposite. V is hypotenuse. Which trig function is that? It's not cosine. We just used it.
Sine.
Yeah, sine. So let's write it down. Sine of what would go in parentheses? Theta equals the length of the opposite over the length of the hypotenuse. What's the length of the side opposite theta? Y. I tried to show that it was a length. And what's the length of the hypotenuse?
Magnitude.
The magnitude of V. So now we're going to do the same thing Jake told us last time. Just move the magnitude V to the other side. And that's going to give you the formula for the vertical, for the Y. So it's magnitude V sine theta. Magnitude V sine theta. Now we can shorten that up a little if we want because we have the same thing written twice. What do we have in front of both trig functions? Magnitude V. So if you wanted, you can write it like this. Magnitude on the outside, cosine angle I plus sine angle J. It's the same thing. You might see it either way. When you're going through a problem, this is going to have to be the first step. You're going to have to distribute this magnitude out. So I usually write it the way you see in the box. If you look in your packet, you're going to see it the way I wrote it down below. Okay. All right, so it's the same formula again. So if they give you the initial speed, so you don't have to write it again. If they give you the initial speed and they give you the angle you're throwing the object at, this is the formula to use. Just remember, alpha is the angle, magnitude of V is the velocity. Okay, so I'm not going to go through an actual problem, just show you in this one. These are the only important numbers. The object is being thrown at 50 miles an hour. You would put 50 right there. It's being thrown at an angle of 30. You would fill in 30 and 30. And now just use your calculator to do it out. 50 times cosine 30, 50 times sine 30. And that's it. We'll go over one when we do the homework tomorrow. Any question on that? Okay. Okay, so homework in your packet, not in the book, on page 344. 25 to 47, just odds, and then 55 and 57. I think 55 and 57 are the velocity ones. So if you get stuck, don't worry. We'll go over them.